Alrighty, for this one we're looking at acceleration, just in general, and we'll see a few things about it here. So, first of all, definition of acceleration is that acceleration is the change in velocity over a given time. So that is the general definition of acceleration. There is one more thing we want to write down here, and that is that the SI units for acceleration are meters per second squared, because we have not seen that yet. So we do need to recall that velocity is a vector, has magnitude and direction. If one of those two things changes, then the velocity is changing. So by the definition of acceleration, if it is the change in velocity, then if the velocity changes at all, whether that's magnitude or direction, then the acceleration is changing as well. So first thing here you want to write down is that the average acceleration is the rate at which velocity changes, and also write down this formula. Another thing we're going to want to write down here, or remember at least, is that typically, not highlighting in red here, typically initial velocity just as before is typically 0. So not initial velocity, initial time. So keep that in mind, because that's going to make things a lot easier for us when we calculate average acceleration. We don't have to plug that in as well. So for this one, we're just reiterating that, again, acceleration is a vector, but it is in the same direction as the change in velocity. That does not mean it is in the same direction as the velocity. So if the velocity changes direction, as in it gets slower, then the acceleration is in that direction instead of it going the same direction as the velocity if it's getting faster. And we'll talk more about that in a second here. So first of all, deceleration. This is a special type of acceleration. Deceleration is when an object slows down. In other words, its acceleration is opposite to the direction of motion. And again, that's similar to what I was talking about earlier. And you can see here in the picture, the plane is moving to the right, so its velocity is moving to the right, and hopefully it is slowing down. If it's not, then we have some problems. But hopefully it's slowing down, which means its acceleration is pointing to the left, and that means we have deceleration, we're slowing down. So velocity is to the right here, acceleration should be to the left because it's decelerating, slowing down. So now on this one, you do want to draw this picture. We're going to have another one of these here in a second, because there's 4 different situations we can have when we're looking at deceleration versus negative acceleration. So for car A here, we have a car that is speeding up. It's going to the right. It has a velocity that's going to the right. It's positive. Because the velocity is positive and our acceleration vector is also pointing to the right, it's speeding up. Both of the vectors go the same direction, it's speeding up. Whether that speeding up is positive or negative depends on which direction it's going. Since both of them are going to the right, it is speeding up with positive acceleration. Our bottom one here, B, the car is slowing down. And the reason it's slowing down is similar to the plane we just saw on the last slide. So this one's velocity is moving to the right, but the acceleration is moving to the left. When those two have the opposite direction, then we have deceleration. So the direction of its acceleration is opposite of its direction of motion. Deceleration, this has negative acceleration. So on this case with negative acceleration, deceleration and negative acceleration are the same thing. In this case only. If they are moving, the vehicle or the object that's moving is moving to the positive direction, but slowing down and decelerating, then our acceleration is moving to the left, and that means we have negative acceleration with deceleration. This next one has our cars C and D on it. Again, draw the picture here. And so now we're going the other way. The cars are moving to the negative direction. So to the left is negative, remember? And if that's the case, then we have a negative velocity. But car C, has an acceleration that's moving to the right. Since, again, our velocity and acceleration vectors move in opposite directions, they have a negative, or they have deceleration, so this is slowing down, and it has positive acceleration. Where is that at on here? Acceleration is positive, there we go. And again, in this case, because it is moving to the left with a positive acceleration, so negative velocity, positive acceleration gives us decelerating, because again, its acceleration is opposite its motion. And then car D finally is our other weird one. So these two are the oddballs, I like to call them, because they do things in a different way than you think they should be doing them. So the first one has positive acceleration. You would think that means it's getting faster, but it's actually slowing down because it's moving in the negative direction. Then car D, same idea, but going the other way. It's still moving to the left, has a negative direction for its velocity, but its acceleration is pointing in the same direction, so that's also negative. This one has negative acceleration, but is speeding up, because in this case, the acceleration is in the same direction as the motion. So that makes it speed up. Sorry, my dog has a weird cough behind us. He's got some issues going on. So here we want to match the term to its definition. I let everybody in class go ahead and do this on their own for a few minutes, but we're just going to jump into it. So acceleration is the rate at which velocity changes. Negative acceleration is acceleration in the negative direction of the chosen coordinate system, and deceleration is acceleration opposite to the direction of motion as an object slows down. So for this example here, we have a racehorse coming out of gate, accelerates to a velocity of 15 meters per second due west. So west is to the left, so it's negative. You can see in the picture here, we have an arrow pointing to the left for the velocity, and it's negative. We want to find the acceleration of the horse moving also to the left. Hopefully the horse is getting faster. So that means we're looking for a negative acceleration here, even though it is getting faster, it's speeding up. So we have everything kind of given to us in the sketch they drew for us here. So we have our average acceleration formula that we wrote down earlier. Change in velocity over change in time, similar to our displacement one, average velocities where we had before. In this case, that is the final velocity minus initial velocity divided by final time minus initial time. And so again, just like before, we have some things that are zero. We should write all this stuff down. It's already written down, but the times are not written down up there, so we'll do that. So initial time is 0. Final time is given to us as 1.8 seconds. So there's the additional details they didn't put in the sketch. So we have two things that are 0. We can go ahead and eliminate them now. Initial velocity and initial time are both 0, so we don't have to worry about plugging those zeros in because they're gone. So we just have our final velocity over final time, which is negative 15 over 1.8. And when we plug that in the calculator, negative 15 divided by 1.8 is negative 8.33. Forgot the negative. Negative 8.33 meters per second squared. I don't know what just happened there, but there. All right, so instantaneous acceleration, another definition for us to write down, is the acceleration at a specific instant in time. And similar to instantaneous velocity, we can't just calculate that without having calculus or specific things given to us like tables, graphs, things like that. So we can't really find it without that information. So here we do have a graph, and you can see in the graph here, this one is a very tight wave, which means it is very close to the average as it is. Whenever you have that happen, whenever it varies very slightly off of what the actual average is anyway, then you can kind of just say that it is equal to the average, because it's pretty much about that all the time anyway. But in the case like this, where it comes off of it a lot, varies a lot, goes positive, goes negative, is all over the place, can't really do that. So in this case, you're just going to look at it in terms of the intervals of time that it's at each velocity. Acceleration, sorry. So the 3 meter per second squared acceleration from 0 to 1 second, and then from 1 second to 3 seconds, we've got that interval we can look at. That's at negative 2-ish meters per second squared. And then back at 0 from 3 to just over 4, and then from there it's up at like 1.5 or so, and then from there it jumps up to 5, and then drops back down to negative. All of those intervals that it's looking at individually is how we would look at the instantaneous for this situation. So we're going to look at some problems with these different trains here. To start off, we're going to look at displacement, and this is kind of a review of displacement from before. So we have this train, we want to calculate the displacement of it moving this way, and if you look close enough at the image, it does give us the work for it, but we're going to go ahead and do that anyway. It doesn't give us the work, it shows us the answer though. So we're looking for displacement. Remember, displacement is final minus initial positions. So looking for displacement, final position is 6.7 kilometers, and initial position is 4.7 kilometers. So plugging those in, 6.7 minus 4.7 gives us a displacement of 2 meters, which is exactly what they have. It is positive, it's moving to the right, so it works out just as we would expect it to. On this next one, the other train, same idea. Looking for displacement. Displacement is equal to final position minus initial position. Final position here is 3.75 kilometers, and initial position here is 5.25 kilometers. Now there is one thing we didn't talk about. They do show in the image here these little tick marks at the top of the variables for each part, and that just is referencing that we're looking at the second part of the motion. So delta x, you call that prime. So delta x prime, xf prime, initial x naught prime. All of those indicate, because I said prime on those, that we're looking at the second part of the motion involved here. So anytime you see that, that's what it's talking about. And if you go further than that, say you're looking at x naught double prime, then that's the third part of the motion. That's the initial for the third part. So we're ready to plug stuff in. Final is 3.75 minus our initial of 5.25, and subtracting that gives us our displacement of negative 1.5 kilometers. So this one here just wants to reiterate that the distances traveled are different than the vectors for these, or than the displacement. So our distances traveled are just 2 kilometers for the first one, which was the same, and then the second was 1.5 kilometers because it was now negative. I would get rid of the negative to look at the distance traveled. We're going to brush over that though. And this talks about the solution to that, exactly as we mentioned. So looking back at that first train, now we're looking for the acceleration. It doesn't say it in the words above in the problem, so I do need to switch over to the teacher side, start this timer, and hopefully we're done before 5 minutes is up, but it doesn't really matter. So this is the problem. We are starting from rest, so 0 to 30 kilometers per hour, and 20 seconds of motion. We want to find the average acceleration in that time. So let's go look at it again here. So the picture is there for us. It doesn't really help us because it doesn't tell us all the stuff like we did before. But again, we're looking for the average acceleration here. So we're looking for average acceleration. And again, this one is speeding up, so it should be going to the right because that's the same direction as the motion. Our initial velocity and final velocity. Initial should be 0, so it's just a point. And our final is 30 kilometers per hour. So that's in kilometers per hour, but everything else is going to be meters in seconds, so we do need to convert that. Time final is 20 seconds, and time initial is 0 seconds. We have everything we need, and the one thing we're looking for, again, using that acceleration, the average acceleration formula, sorry, I didn't draw the arrow for that as well, is the change in velocity over change in time, which is final velocity minus initial velocity over final time minus initial time. And again, we have some things that are 0. The initial velocity and initial time again. So we have the final velocity just divided by our final time, which is 30 kilometers per hour divided by 20 seconds. We do need to convert that. We wouldn't do that up here, so 30 kilometers per hour, that is in 1 kilometer, there's 1,000 meters. And so that eliminates the kilometers part. And then in 1 hour, there are 60 minutes. In 1 minute, there are 60 seconds. Oh, that's going to delete everything I just did. My hand just brushed the arrow. So that's unfortunate. So final velocity is 30 kilometers per hour. I'm just going to tell you what that is in meters per second now. But basically, we would multiply across, get 30,000 divided by 3,600. And that would eliminate the zeros. 300 divided by 36 gives us 8.33 meters per second. And again, that is going this direction. Initial velocity, 0 meters per second. Final time is 20 seconds. Initial time is 0 seconds. And acceleration is pointing that direction, and we don't know it. There we go. Write all this out again. I think that's the first time I've ever done that too. Worked on Nearpod a lot and never just brushed it with my hand while writing. Didn't know it would do that while I was writing. And eliminate the things that we know are 0. So final velocity over final time, which is just going to be that 8.33 over 20. So I'm going to go ahead and show this on the calculator here. So again, 300 divided by 36 is what we would have ended up with, which is that decimal. I didn't mean to have the X there, sorry. iPad slid down on me. Divide by 20 is 0.417 meters per second squared. There's our answer. So again, we did get a positive acceleration as we should have. It is moving to the right and accelerating to the right. So there we go. Now this next problem, still looking at acceleration. This time it is slowing down. So same idea, but now our initial velocity is that 30 kilometers per hour, which we know now is 8.33 meters per second. And that is again moving to the right, coming to rest, so our final velocity is 0. Final time is, I can't remember, what was it? Oh, it's going to show me. It's 8 seconds. There we go. I finally remembered. And initial is 0 seconds. And acceleration, again, is what we are looking for. So average acceleration is equal to change in velocity over change in time, equal to final velocity minus initial velocity over final time minus initial time. And again, some things can eliminate. This time it's the initial time and the final velocity. Those are both 0. we have negative initial velocity over the final time, which is negative 8.33 divided by our time of 8 seconds. Now remember, in this case, it is decelerating, slowing down, so it should point, our acceleration vector should point in the opposite direction of the velocity's vector or the motion of the object. The object's moving to the right, so our acceleration vector should point to the left. And that means it should be negative, and we do get a negative here. We get a negative 8.33 divided by a positive 8. That gives us a negative 1.0417 meters per second squared. So now we're going to look at some graphs of this situation here. So this one, our train is moving with an acceleration in certain parts. So this graph looks at acceleration versus time. Doesn't really tell us much more than that, aside from that it is moving at constant velocity at one point as well. So that first portion up here is constant acceleration from 0 to 20 seconds. So that's the acceleration we saw earlier, which was 0.417 meters per second squared, which is where it's at. Straight line right there. Then at 20 seconds it stops and goes a constant velocity, zero acceleration then for 20 seconds, and that's why it's at zero. There's no acceleration. And then it drops from there down to negative 1.0417, which is exactly what we got for the second graph, or second calculation. This next graph is our velocity versus time graph. Remember, for this one though, the slope of the curve for a velocity versus time is the acceleration. So this one was accelerating to start, and that's that positive slope going up from zero. That slope, if we were to find it by using rise over run or whatever, would give us 0.417 like we had as our first answer. And then it's again positive, so it's going up as we go to the right. And then it has that flat portion, which has a constant velocity of 8.33 or 30 kilometers per hour. And then it starts to drop from the 40-second section. That is our negative 1.0417 we just got on the last problem. It's got a negative slope, which makes sense again because it should be negative. And it is a steeper slope as well because it is decelerating and slowing down faster than it accelerated up to that 30 kilometer per hour speed. Then we have this graph here. This is a position versus time. This is a bit different, but notice there's still things we can get from this. In fact, we can't tell exactly what the acceleration is, but we can tell that it is accelerating. So from the first part, from 0 to 20 seconds, it's got a curve to it, right? So it's going up as it goes to the right. It's curving to that, and it's getting steeper. So that means a few things. Position versus time graph slopes are velocity. So if the velocity is changing, that means it should have a curve to it because the slope is constantly changing, which means it should have a curve there when it's accelerating, because change in velocity is acceleration. So if the velocity is changing because the slope is changing, then it has acceleration. So that first section from 0 to 20 seconds is curving because it has an acceleration. And then it reaches that 20-second mark, and now it has a constant acceleration, or constant velocity, of 30 kilometers per hour, or 8.33 meters per second, and that is the straight section there from 20 seconds to 40 seconds. And at 40 seconds it starts to decelerate, so now notice it starts to curve again. But this time it's curving back down and flattening back out because it's getting to where it's got a constant velocity of zero because it's coming to a stop. So this one here, we're looking for velocity now of the train that we saw for the second train. This is the one that was going to the left. So this is our average velocity that we're looking for, which is just displacement over time. Remember, this one's moving to the left, has a negative displacement of negative 1.5 kilometers, and it has a time there that tells us it takes 5 minutes to do that motion. So we have our choice here. We can do one of two things. We can convert both kilometers and minutes to meters and seconds, or we can convert the minutes to hours, and that's going to be the easier option because it's just one conversion. So let's do that. So in 60 minutes, that is 1 hour. So that means we're going to divide 5 over 60, which gives us 1/12 hours. So 1/12 of an hour. So now we have everything we need to plug in. Average velocity is negative 1.5 over 1/12. Remember, when you divide fractions, you keep change flip, so you keep the first one the same. Change division to multiplication, and change that 1/12 to 12, and or flip that 1/12 to 12. And so we're multiplying that. Pretty simple. 12 times 1 is 12. 12, half of 12 is 6. 6 plus 12 is 18, so it's a negative 18 kilometers per hour. Now, there is a cheat for these. So, there's a cheat to convert from kilometers per hour to meters per second. So remember on that one problem we did the 300 divided by 36. Well, that simplifies to be, ignoring the 30 that we plugged in, that's why we got the 300. But 30, or the 100, let's say, would be 100, be 10, 10 over 36. Simplifies to 1 over 3.6, which means if you divide kilometers per hour by 3.6, so negative 18, divided by 3.6, it gives us our velocity in meters per second. If I want to go the other way, so if I had done this the other way I mentioned, 1500, well, it'll be negative. The 1.5 kilometers would be negative 1500 meters, and we would divide that by the seconds, which 5 seconds, 60 seconds per minute, 5 minutes. Multiply those together, you get 300 minutes, and you get the negative 5 both ways that I just did. So either way, it would also be negative 5 meters per second if that's the way you would want to go, or if that's what it was asking for. But really, if any situation, if you have a problem given to you in kilometers per hour, you need it in meters per second, divide by 3.6. If you have it in meters per second and you need it in kilometers per hour, multiply by 3 points. Oh my goodness. Multiply by 3.6. So this one here, I believe this is our last problem. We are going to look at deceleration of the same train. And in this case, again, we have the initial velocity, bring that back down, is 20 kilometers per hour, which we now know how to convert that easier. Final velocity, though, this is decelerating to a stop, so that is in meters per second at 0. And then initial time is 0. Final time, it doesn't say it up top, but it is in 10 seconds. And we are looking for average acceleration. So again, this one is moving to the left, so that is a negative 20 kilometers per hour, which also it is decelerating, which means we should get a positive acceleration out. So average acceleration is equal to change in velocity over change in time, which is average velocity, final velocity minus initial velocity over final time minus initial time. We have two things that are 0 here as well. That is the final velocity and initial time. So once again, we have the negative initial velocity over final time. We're ready to plug stuff in. Negative 20 divided by 10 seconds gives us 20 over 10. Oh, it's not 20. Hold up. I forgot to convert. So we need to convert that 20 kilometers per hour. I didn't do that. So 20 divided by 3.6 is 5.56 meters per second. And that should be negative as well. Forgot that part on there too. Negative 5.56. So going ahead and doing this here, we've got the minus 5.56 divided by 10. The negatives are just going to cancel each other out. And dividing anything by 10 just moves the decimal place over 1 to the left. So average acceleration is 0.556 meters per second squared.